Now let's go on to look at another common porosity tool, the neutron log. We recall that the neutron log responds primarily to hydrogen atoms in the formation. The two elements of a formation with the greatest concentration of hydrogen atoms are water and liquid hydrocarbons that occupy the pore spaces. Thus, in clean formations, the tool reflects the amount of liquid-filled porosity. Neutron porosity readings are computed automatically and displayed as a curve scaled in linear porosity units similar to the density porosity display. Neutron readings are affected to some extent by the lithology of the matrix rock. Therefore, a matrix setting must be chosen prior to logging the well. Neutron logs, however, are usually scaled for a limestone matrix, and if the actual lithology coincides with this chosen matrix setting, porosity may be read directly from the log. We know from cuttings information that this formation is limestone. Thus, here we can read porosities directly from the log, 5.5% here and 13% here. Porosities for lithologies other than limestone may be determined from a chart, but the actual lithology must be known. Let's look at a compensated neutron log run over an interval that we have determined from other data to be sandstone. First, we note that the log is scaled for a limestone matrix. We therefore cannot read porosity directly from the log, and we must use a chart. Here, our curve reads 15% apparent limestone neutron porosity. On our chart, we go up from 15% on the apparent porosity scale until we intersect the sandstone line, then across to find the true neutron porosity for sandstone, which in this case is about 19.5%.
Two common situations will cause the neutron porosity log to give false readings. These are the occurrence of gas and the presence of shale in the formation.
Water and liquid hydrocarbons contain about the same amount of hydrogen per unit volume. Gas, however, usually has a significantly lower hydrogen concentration than these liquids. Therefore, when gas is present in the pore spaces, the neutron log reads a too low porosity. In addition to seeing the water in the pore spaces of a formation, the neutron log also responds to the bound water associated with shales. In general, shales have a large apparent porosity because of their significant hydrogen content. This causes the apparent neutron porosity of shale formations to be greater than the actual effective porosity, as indicated here by the density log.